Hello everybody. I'm going to introduce a new geometric view to data analysis. ST-metric is a new method. This is a metric defined on n-dimensional cube. It is generalized from a probability metric which is defined from entropy. Overview of my talk. Motivation. This is about where the idea came from. I will introduce the definition entropy and link to the ST metric, some properties of ST metric, and the second part of my talk is all about applications to the finance. A few years ago, I faced with the following problem as a researcher, not as a fund manager. Each curve in this graph represents an investment strategy. Question is, how can we order their performance based on their return values? As we see, some of the curves are so close to each other. How close of the curves shows us that we can assume the performances of their corresponding strategies are the same. Entropy, definition of entropy is here. We have x and y, random variables. P and Q are corresponding probabilities, and the Shannon entropy, or simply entropy, is given by this formula: negative values of the sum of all pi log pi's. Entropy measures uncertainty. It is used widely in science, thermodynamics, physics, information theory, and ergodic theory of dynamical systems. I view entropy from information theory point of the view. I refer to the reference, the book of Cover and Thomas on information theory on that context. Another concept, relevant concept, is relative entropy. Relative entropy has also different names of it: Kullback-Leibler divergence, Kullback-Leibler information criteria, or simply KLIC. Here we have two probabilities and pi log pi divided by qi. It is discovered by Kullback-Leibler in 1951. This is used to approximate a distribution to a given data. The key here, this is not a symmetric value, so dpq is different from dqp. And also it's not a true metric because the triangular inequality fails. So Jeffries, to avoid this inequality case, introduced the concept of the symmetric extension. It's also called J divergency or Jeffries divergency. It's introduced in 1973. Just summing up these two values. So another relevant concept will be if you take the P and Q to probabilities and average of them, midpoint them, and take the symmetrized of the relative entropy and then sum it up. And this distance is called the Topsoe distance. It's introduced by Topsoe. This is not a metric, but it is square. My contribution in that context in 2017, the square root of Topsoe distance is also a metric real metric if we take the values from the 0, 1, but do not require the sum is equal to 1. It's not a probability space anymore. Still the values are needs to be from the 0, 1 this interval, unit interval, but the summing up equal to 1 requirement can be the summing up all PI's for a probability has to be 1, as we know, or for the this is a second property for the being a probability. You can remove this property and still you will have a metric. That's what I'm trying to say. So it's just this is a definition, as I said, same as before. This time you have the values from the unit interval 0, 1, and this is the midpoint, symmetrized, take a square root. So this is exactly the square root of the subcellular distance. This is why I used the ST. ST is corresponding to square root of a subcellular distance formula. So this is a real metric. It satisfies symmetric conditions. It is positive. It is symmetric. It has triangular property. It is always positive, and it's particularly 0 if every point PQ are exactly the same, and the symmetric, and also we have the triangular property. So it is a true metric between two discrete planes, curves in endpoints with the values 0 and 1. So basically, since it is a discrete, we are talking about the points as a curve, but in order to be able to visualize, we are smoothing when we are working usually to see what is going on. So I work it out with the certain values, certain distributions, looking at the certain distributions with the ST metric. If we have as an example, cumulative uniform distribution UN will be I over N for each. This is the time, and this represents the values. So uniform cumulative uniform distribution will be the blue one, which is just think of square, and then the diagonal line will be giving you uniform distribution. And this one here, the orange one, is the Lorentz curve, which is pretty close to the uniform distribution. Another closed case occurs as a normal distribution, which is the green one here. The others are giving you the extreme cases. They are really different. So by using the normal distribution or Lorentz polynomial or Lorentz curve together with the uniform distribution, I would like to express that they are close enough curves, corresponding close enough distributions for the data. So if we have certain values, for A is this value, normal distribution, and the Lorentz distribution will be in a similar pattern. This will be go like that, this will be go like that. They are smaller, close to the uniform distribution. With this view, we can calculate for each n data points, we can calculate the ST metric for the uniform distribution to Lorentz or the normal. We will find a value. These kind of values for each data can be used as a critical points or criterium to establish a criteria to saying that if two strategies are too close together, if it's equal or smaller than these two values, if you're looking at 1,000 data points or more. So the second nice thing about this ST metric is the fluctuations. Now, if you this is the uniform distribution. It does and at this point will get dense with respect to the how many data points that you're taking. So n gets larger, you will get denser point sets here. If we think about two sets, but one of them is uniform distribution one, another one is just in one point there exists an epsilon addition, right? In one point. So I denote this set by the k. So at the point k, I am adding an epsilon. So that will create a fluctuation to up here. If I subtract it, I will have a fluctuation down. So if I do that, I realize this is what I proved, is that the ST metric differs for these values. Everything is exactly the same, but the up value, the ST metric that you're getting from this picture is different from the ST metric getting this picture. So this property I called structure of fluctuations. And the timing of fluctuation differs in ST metric case as well. If you so the time is the x-axis. If your fluctuations happen here or fluctuations is happen here, differs. Same epsilon, up or down, but the timing of the fluctuation will make big differences. So the k is a point here, the time point. L is the time point. The fluctuations that happens here will be higher, having a higher ST value than the fluctuation that happens in exactly the same way here. So structure, the going up or down in the ST metric differs. For the timing, it differs. And the magnitude of the fluctuations, it differs as well. If epsilon 1 and epsilon 2 are two different magnitude, if you have in the same point, in exactly the same point, one is smaller and one is larger, it will give you a different ST metric. Since everything is positive, of course the bigger one will give you the bigger value. For the magnitude, and the quantity of fluctuation will differ as well. If you have more fluctuations, right, in one of them, and then if you have less fluctuation in another of them, it will differ. So fluctuation, ST metric, really gives you more information about the fluctuations. For example, if you think about the L1 Euclidean distance case, just the absolute value and summing up those values, then by looking at this particular set, UN and 1 point fluctuations, if we looked at the UN and 1 point fluctuation, we will always obtain epsilon. Nothing different. It could be here, it could be here, or it could be here. It doesn't matter for L1 Euclidean distance formula. It will always be the epsilon. It's always epsilon for Euclidean distance, and it's also, but it's different for the ST metric. Further, if you looked at the, so the L1 is always epsilon, and no information on the structure and the timing if we looked at the L1 Euclidean distance. No information, but in the ST, it will give us the different values. In the case of magnitude and the quantity, they are the same values. So L1 values, also epsilon 1, epsilon 2, will give us exactly the same inequalities. So what I'm trying to say is that the L1 for magnitude and quantity, if we change the quantities and we change the magnitude, we will get some information for L1, but for structure and timing we have no extra information for L1. It's the same thing for L2. We will always have epsilon for going up or going down case, always epsilon. This distance calculated as an epsilon. So it is just if we change going up or going down will not change. So structure and the timing, and also if you change the place, the timing, and or down case, they are all epsilon for L2 distance, but these are all different values for ST metric. And the inequality for the magnitude for epsilon 1, epsilon 2 for the large ones will, and the quantity, the same equalities as we had for the ST metric will hold for L2 metric. So the differences in structure and timing gives the structure and timing issues. ST metric gives different values. L2 metric and L1 metric are the same. Does not give you any information at all. ST metric is complete as it's discrete, and ST metric does not define. This is just a little notes here that I took. I'm looking at the structure of ST metric spaces, what it holds, what it doesn't hold. It's just a structuring, discovering further ahead about the ST metric spaces. Okay, just complete as discrete. ST metric does not define a norm. Scaling property fails, as it is here, as I showed here. If you have alpha in 0 and 1, it does not go up as an absolute value of alpha. It has to be square root, but with respect to this inequality, we cannot have a norm, we cannot define a norm, we cannot put it. And of course, since we don't have a norm, ST metric space is not a Banach space. And if we have two probability spaces, then this holds. I think for any PQ in 0, 1, this holds. Maximal invariant transformation. So since we have the data in finance, it is not necessarily between n0 and 1. So our requirement is to be in the unit interval 0 and 1. Well, we can include the 0 if we assume that the log 0 is equal to 0 for a convention. If we do that, we can include the 0, 1 in all our definitions. So in general, the data points is different from the 0, 1 in finance. So, but we can transform any return series data into a 0, 1 by applying the maximal invariant transformation. For reference, Lehman-Ramanon's books in section 6 talks about that. Why this is important? Because this kind of transformation respects do not change the distribution, which is important, and also do not change the timing. So the timing, how this data appears, would not change, and or the order of the timing would not change. And also by applying this transformation, we will obtain all this financial data, various from many real numbers goes into the 0-1 interval. Okay, what is this transformation? First, I can transform by adding a constant. So have your return data series, your data, add to the minimal to the data, then everything will shift up above the 0, but still we will have some values above 1, so we need to squeeze. For the squeezing, we need to divide. If we are adding certain numbers to the all data, or if we are dividing certain numbers to the data, this is the maximal invariant transformation, which will not change the distribution structure. Once we do that, and we looked at the ST metric, this is the application for performance measurement. We take the all transform cumulative returns into a set like AIJ. R is the cumulative returns of the risk-free rate. So taking one certain return, which are assumed to be the risk-free rate in the finance. Everything else, any risky assets investment, should be above that, right? So in finance, if you have a data risk-free rate, if it's here, all the other data should appear somewhere here, because this is risk-free. If it is risk-free, anything is risky should be above that. That is the idea in finance. It's what's assumed, right? All the other data should appear here. Okay, with this idea, taking a risk-free rate, it is an assumption. It is not a practical. Actually, people assume that is a risk-free rate. Sometime before the financial crisis, people were thinking that the bonds were the risk-free rates. Now, is the interest rates, the base interest rate can be assumed as a risk-free, and so on. Whatever your risk-free rate asset is in your favorite one, let's take that one together with your transform cumulative returns, calculate the ST metric, and find out the ST metric in ascending or descending order, and decide which strategy perform better than the others. In order to be able to decide the equivalent ones, use the idea of critical points to calculate the uniform distribution together with either normal distribution or the Laurent curve. For a Laurent curve is defined as Lx, x is equal to x to the power a for this particular power a. And UN is the cumulative uniform distribution. That's if we have the 0-1 and 0-1 as the diagonal. If you have n data points, you calculate the ST metric between UN and the Laurent's curve. Laurent's curve will be something like this here to calculate, and for data points, this is a certain number. This will be a certain number for each n. So you can use this as a criteria to decide which of the strategies can be assumed as equivalent, right? Lorentz curves will look like this, and so this is the result from the first slides that I showed. So you have the ST metric result, and you have S1 and S2 values. S1 is the scholastic dominance method to decide which distribution are close, and we can assume it is we can assume that it is the equivalent, approximately the same distribution. S2 is the scholastic dominance method 2. And here what I would like to show is that by taking the A 1.16, 1.2, 1.13 and up to the 2, I've calculated the ST metric values, right? For ST metric value, so this is the value if two strategies are close with that value, I will assume that definitely they are corresponding the same. All the other values are different for the method that I'm introducing. We can still order for those values all these strategies. For the scholastic dominance method, we will have for scholastic dominance method, you have 1.7, 1.6 are the see the p-value here is 0.05, 0.02, 0.05. These are the p-values. It assumes that scholastic method, first order scholastic method, assumes 1.7 corresponding to 1.7. So this is 1.6. The blue one is 1.6. Right? And this is 2. This is 1.6. This is 1.8. So these are the curves that the scholastic method assumes are the same as the uniform distribution. So these curves and these curves represents the same strategy, same distribution according to this one, and this one represents the same distribution according to scholastic dominance method. The method that I have introduced says that no, they are different. The ones with this one and this one are the same, approximately the same distribution, but they are these one and these ones are different. So this is what it is. This calculation, what that shows. These are a particular cases shows that ST metric, for example, looks at this curve, calculates it, and says that they are distinguishable. And so the first order scholastic dominance method thinks that they represent the same series, same distribution. As we see here, huge differences. I mean, this is scholastic S1 and S2. S2 is probably that one. S2 is 2. S1 or S2 scholastic dominance method around here says that they are the same. This one and this ones correspond the same distribution, and ST metric says no, this one and these ones are the same distributions, but these are the different distributions. Okay, ST metric and the mean variance theory for risk-averse investors. mean variance theory and ST-metric methods are they agree. So ST-metric method agrees with the mean variance theory. If we take the R as a cumulative distribution of the risk-free rate and calculate and define the utility function as ST-metric, your investment and together with the risk-free rate, it gives you the utility function. And this utility function is monotone increasing for each R values. This lemma is very important. If we say this thing is very important for each point, the risk-free rate, the return of the return series for each point xi should be bigger than the ri. This is a huge assumption. This is not the case in general. In practice, this may not hold, but in theoretical sense, if we think that any risky asset always has a return more than the non-risky asset, that's the definition of the risk-free rate. If we have a risk-free rate, it means that there is no risk. If there is no risk, there is no for the risky assets, return should always be bigger than that. If this is the case, this lemma says that the function u is a concave function. Why being a concave is so important is in the next slide. Since it's a concave, it satisfies the mean variance theory for risk-averse investors theorem. If x and y are random variables, mu are the returns, expected returns, and sigma are the variances, which corresponds to risk in financial data, so that any utility function non-decreasing and concave, then the expected value of the utility function is bigger than the expected value of the utility function of y. This means that the mean mu1 is bigger than mu2, while sigma 1 squared is smaller than sigma 2. This means that the higher the return, the smaller the risk. So this is the best investment option. It is required for utility function to be concave, and the utility function defined by using the ST metric satisfies this condition. This leads us all to in finance. There exists a huge section about the utility functions, so portfolio management, optimization of or hedging related with the utility functions, all can be applied to this function, this utility. Since it is non-decreasing and concave, it satisfies this condition here. So the next application is about a factor exposure. That's the and what is factor exposure? We think, and these are the factors, systematic factors like value, size, quality, momentum, or minimum volatility. Factors that affects to the prices or affects to the returns of the investment. ANG and his group in 2018 decomposed the major market indices into those style factors by using the exchange traded funds as a liquid assets. They use the tracking error, that is the standard deviation times the tracking differences, as objective function in a factor model to find the factor weights of major indices. So approximation. So yeah, let's have a look there. This is from their paper. All over there are so many countries. They looked at the certain products, and they looked at the momentum, minimum value, minimum volatility, value, size, quality, and these are just basically weights, right? They are looking at the weights, and they are looking at the factors. So factors here, just 5 factors models, right? I is equal to 1 to 5. You have the WIs by just looking at the calculating the you want to find the weights corresponding under certain conditions. They are looking at the trace error for their calculations, and calculate the W's. So these are basically corresponds the weights of these factors correspondingly to these in products, finance products. So I introduced the method. We introduced the method with Tony Hall and Nadima El Hassan, using the ST metric rather than the tracking error method. Here we have risk factors. We have only 5 risk factors, but depending on the time, and W's are the weights corresponding to each factor. So since the weight has to be the one, we want all of them positive, and benchmark return is the denoted by BT, and the PT is the portfolio that we constructed with the factors together with the weights that we calculate. So there exists a certain time period. We looked at the data, how close they are. Tracking error method calculates the sigma is the standard deviation with the differences between PT and BT, and take the absolute value of the PT BT over your time period, and minimize these differences, because you want your constructed portfolio come close to the benchmark. As close as possible gives you the better expectation. So your optimization is minimize this and find out the weights WT. So we introduced that we calculate the weights by taking the minimal on the ST metric rather than this condition. Instead of this condition, we replace this condition with the ST metric, minimization of the ST metric. And the outcome, I just would like to show you the outcome. This is the data that we used. Australian market. In Australian market, the benchmark was the AUMF, Exchange Traded Fund. And these are the factors corresponding these are the price indexes of the different financial products and the corresponding risk factors. This is the data that we used, and this is the outcome. So we've looked at a different type of error. Forecasting error or weight error. Forecasting error is looking at the last. Forecasting error calculates the differences between the benchmark and the forecasted value of the portfolio that we constructed. Weight errors is the actual weights and actual weights and calculated weights. So what we've done, we take the certain values like 6 months for the calculating the W's, and calculating we calculate the W's for the 6 months, and then using these W's we construct the 7th month data. So the price that's constructed with this is the forecast error, or the weights that we constructed for the last period, how it fits, is the weight error section. So the experiment 1 is the 6-monthly experiment. Experiment 2 is a 3-month experiment with averaging weights over the 3 months. And the experiment 3, 3-monthly experiment with a fixed set. So I have a choice, since I have 6 different weight system here. For the 6 months, I take the average for the, I took the average of this. I calculated WIs, we calculated WIs for 6 months, and then taking the average of them and to use that weight into the 7th month weights. That is the experiment 1, and experiment 1 for 6 months, experiment 2 for 3 months. Experiment 3 corresponds the same 3 weights. It has been calculated for the previous data and looked at the 4th month and used the same weights for this. And let's have a look what is the error messages that I'm getting. So this was the what is experiment 1, experiment 2, experiment 3 represents it here. The success rate for the ST metric is a lot higher than the TE. So I've done these cases many times. So each time that I am, if ST metric got better results than I recorded, or TE method get better results that I recorded, this is the success rate of ST metric method over the TE method. And it's the similar idea we've done for another data set for the US market. This is from another data set, and still success rate of ST metric is over the TE is really higher. Some of them always ST metric gave a better value, better values, better estimations than the TE methods. Why? This is just one demonstrations in terms of the graphs tracking the UMF with respect to tracing method is the blue line, and the AUMF is the actual data, financial data graph, and by using the ST metric, the tracking AUMF, and this is the red one is the actual AUMF financial data set, and the tracking AUMF, how it follows with the ST metric. This is understandable by giving that ST metric really respects, very sensitive to the fluctuations. This is really coming from the idea here that it shows, the theory shows that this is what's going on. Yeah, the theory says that it's the fluctuations are, magnitudes of the fluctuations are different, quantity of the fluctuations are different, and the structure of timing is different. All this fluctuation sensitivity give rise to what we have in the end. And also we've seen here L1 distance will not make a difference. Even the AMG and his group used sigma. Yeah, they used the sigma here to normalize, to make a better estimation. That was the key point in their work. They introduced the sigma as a tracking error method to make the differences. But as we expect, a stereometric method will work better because a stereometric really respects the fluctuations. And these are the some references that I referred during my talk, and the main idea, how the stereometric idea grow basically in this paper. And thank you very much for your attention. Thanks a lot.